My name is Christina Lee, and I'm here to talk about working across platforms, and specifically, this is supposed to give you a guide to just judge the heck out of cross-platform technologies. It is very specifically not an opinion piece on cross-platform. It is a deep dive into architecture of your various choices so that you can make your own opinions. Now, just to spend the first couple minutes to make sure that we're all on the same page, if I'm going to talk about cross-platform technologies, I better define what a cross-platform is, and that leads us to what is a platform. And we define 3 common front-end technologies, which is Android, iOS, and web, and if you really want to be an overachiever, you'll throw MWeb in there as well. Now, what does it mean to be cross-platform then, if this is what it means to be a front-end platform? Well, cross-platform means taking a piece of code and sharing it across 2 or more of those platforms. So, pretty self-explanatory. That begs the question, why would you want to do this? Well, if you are like most companies, you might not have infinite developer resources, and you may have like 1 or 2 or a few developers, and you ideally would want to reach all of these platforms. Now, this is pretty perplexing because, of course, one person would be stretched pretty thin trying to do this, so you might start to narrow down your scope and like drop MWeb. Who needs MWeb anyways? Just kidding, we love MWeb. And you know, you actually probably seen this pattern in Silicon Valley a lot, which is that actually you drop everything but iOS. It's so great. We as Android developers love this. It's our favorite. And you know, it can be frustrating because we are Android developers at this conference, but there's a really good reason that people start with a single platform, and it's because even one platform takes a hell of a lot of resources. When you start adding a second one, you get double that time commitment, and you know, that usually means that you have to increase staffing, and given what most people are paid in the tech industry, we know how well that works out for a company's bottom line. So to encompass this in general, we have this reach that we desire. These are all of the platforms and all of the users that they reach. We want all of them, but most of us only want to pay for a small subset of the complexity it takes to reach those people. And so we get this huge chasm where we introduce something like cross-platform to bridge that gap. So in my idea of cross-platform, it all boils down to answering a single question, which is, how do we increase reach without increasing cost and complexity? Or the alternative to that, if you've already scaled, is how do we maintain our current reach without, or by reducing our current cost and complexity? Now, it's worth mentioning that cross-platform technologies are not the only way to do this. You can also prune features or simplify your app, make the platform easier to build for, you know, build a business model where if you only reach Android, you're still raking in money. So if you know one of those, hit me up, or you know, any other number. But of course, there are drawbacks that come with each of these. So the first is that you can't prune away everything, unfortunately. Google's hopefully working on the Android being easier to develop for with Jetpack. And then, of course, going all in on a single platform can be pretty risky, so you don't always want to do that either. And this is what makes cross-platform pretty appealing to people. And when people talk about it, it's usually in the context of we can reduce all of these timelines and all of these code bases into a single one, which has the knock-on effect of hopefully being able to reduce all of us as developers into a single developer. And if most people have a theory of more money, more problems, the cross-platform motto would be less code, less problems, in theory. Now, this is interesting because I think most people can get on board with why cross-platform is theoretically exciting. Less money for less developers, less code bases, less timeline, but that can be pretty existentially threatening to the people whose jobs are being condensed down, like us. And so it can lead to a lot of arguments that are maybe not grounded as much in the architecture of the different cross-platform technologies as they might be, and are more in feelings or preferences or any of those other things. And so what this talk is doing is I'm going to take the time to talk about the funnel of how you can narrow down on a cross-platform technology, and then talk specifically about how these technologies are architected so that you have the ability to evaluate them on your own based on the way they're architected, not on preferences or like what your favorite language is, but specifically based on how they communicate, the building blocks within them, and what that makes them good at and where it makes them weak. So to start at the top of that funnel, before you go into the architecture of a cross-platform technology, you probably want to figure out what type of technology you want. There are two big buckets for these. One is sharing logic and one is sharing UI. Although these the UI sharing ones usually include logic sharing, I don't know of one that's only sharing UI and then the logic is implemented natively. Someone is for sure going to now tell me that one exists, so I welcome that. You can tweet at me. But to talk about the logic sharing group, the best part of them is that they're considered easier to get right. And the reason they're considered easier to get right is that the view rendering pipeline and the view layout is a very, very complex system. And if you can share code and kind of throw that to the side and not think about it, then your job gets a lot easier because the business logic is logic that you control. So if you are only sharing logic that you are responsible for, that you can write, that you can test, that you can validate, it narrows that scope dramatically, and narrowing scopes usually means that you have a higher likelihood of succeeding. But the trade-off to narrowing that scope is that you don't get that true reduction in cost the way that you might if you shared UI as well, because of course you can share your logic, but now you still have to have front-end developers for all of these platforms to bind your shared logic to the UIs that are native. So you would have to write your Android UI and use the shared logic, your iOS UI, etc., etc. On the other hand, if you choose a solution that goes with sharing UI, you get really close to that idea where you write once and it runs everywhere. So you can theoretically run your app and you have no front-end developers for Android or iOS or any of the other platforms that you're targeting. I say in theory because there's always at least something that needs tweaking, even in solutions like this, but you can get really darn close to that resource minification that's the ideal for a company's bottom line. The problem with something like this is that it introduces all of that overhead of the view system, of figuring out what to do with this very, very expensive and complicated system that other people up until now have been paid to get right, while you could ignore it and just say, like, draw a view, and then it magically appears on screen. And specifically, this is stemming from the fact that the Android UI and the iOS UIs, or whatever other platforms you're trying to do cross-platform, they are not the same. So you cannot emit an Android view to an iOS platform and be like, hey, iOS, like, here's my Android view, do something. And likewise, Android won't accept iOS views, and so this is the crux of the problem, is that you want to write it once and have it go everywhere, but they speak in different languages. So that brings us to this mid-level consideration in our winnowing funnel, which is what type of cross-platform UI are you, if this is applicable to you, saying that you go with the UI sharing. And there are two big buckets here too, which is that you can be the type of cross-platform that re-implements, or you can be the type of cross-platform that wraps UIs. If we look at this re-implementation case, there are again two questions. I don't know what it is about the number two. Apparently everything is coming in twos today. So two questions again, which is, can you get it exactly right? And this goes back to what I was saying of Android, as an example, has 10 years of history in this regard. That view file, if you've ever gone and looked in it, is like thousands of lines long. It's very, very scary place. I think in The Lion King, that was what they were talking about when they said don't go to those dark corners. The view file has a lot of logic, a lot of history, and so if you want to take on the task of re-implementing that, you better get it pixel perfect, and that's a really hard task. And even if you get it pixel perfect for both Android and iOS and any other platform, then there's this question of, can you keep it pixel perfect? Because none of these platforms are staying still. Every single year they're changing. And so these are two pretty hefty questions, but of course the wrap case has its own drawbacks as well. And specifically wrapping, by wrapping I mean you have your native view and then you have some layer that surrounds it and you're talking with that layer and then it's forwarding instructions down to the Android view or the iOS view in these examples. There's a layer of redirection, as you just heard me describe. There is that wrapping layer, and so now you get into the question of, well, can I do that efficiently? We used to just be able to talk directly to the native views, and now I have this layer of misdirection that is doing some sort of translation communication, and that begs the question of how long is that taking, what sort of resources is it taking, and it suffers from the same problem as re-implementation, which is, can you keep these up to date? So if they put out more components, are you going to be on the hook for maintaining them? The answer is probably yes. And can you do that in a timely manner? Can you always commit the resources to make sure that you're up to date? Because otherwise you are up a creek without a paddle. So this is like extremely high level stuff. This is kind of where we are in this journey. And I think that most of that is not very controversial. A lot of people have already done these evaluation matrices of like, should I cross-platform or should I not, UI or logic, wrap or reamble. And you can kind of get to this point pretty easily because this encompasses the business argument. So there's probably someone at the top of your company who's saying, I want cross-platform to reduce resources. And this will get you into this spiral. But then there comes a point where you get to these terminuses. Is that the plural of terminus? I don't know. You get to the end of these, and this is where things get a little bit more complicated. Because now you might have bucketed yourself into a different group, but you need to start evaluating actual frameworks. And so this brings us to that lowest level of evaluation, which is what specific framework are you? And it's really important that you don't try to evaluate all frameworks, because if you're doing a good job at evaluating the framework, you are evaluating a lot of different considerations all the time. And this is like 5 or 6 of 10,000 that you will probably have to go up for if you go into an architecture review at your company. People are going to ask you so many questions. The saving grace of getting to this point, if you've already winnowed down and now you know that you want to be a UI and logic sharing, re-implementation, cross-platform technology, is that most of these questions, when you get down past the business case, come down to how things are architected. And if you can understand the way something's architected, you can usually speak to whether it has performance issues or the potential for performance issues, whether it'll integrate well into your build chain, etc., etc. So with that, I want to talk about some of our possibilities, which are, React Native, Flutter, C++, and 500,000 of your favorite other friends. I tweeted about this and literally heard so many new technologies that I had never ever known about that it was mind-boggling. So apparently this is what people do on their weekends, is they create new cross-platform technologies, which I'm totally happy for. But because I can't cover all of those, I'm going to focus in on a few of the popular possibilities to go through their architectures. And the C++ case, people usually end up here not by free will, but because there's a really driving performance critical business need to be there. So I'm going to kind of shunt that to the side because if you're there, there's a reason you're there, and I'm not going to be able to pull the escape hatch for you. So let's take a look at these 3 in particular. We're going to start with React Native because I happened to type it first when I was building this slide. And if React Native had a baseball card, it would look something like this, which is that its language is JavaScript or any of the derivatives. So you can use TypeScript, PureScript, or Flow to kind of gloss over some of JavaScript's quirks. It's sponsored by Facebook, but open source, as will be all of these that we evaluate. And the type is UI plus logic, and its claim to fame is hot reloading, which is the developer experience. I think most of you are probably aware of hot reloading, but it basically means that you don't have those 5, 6, 7, or if you're Facebook, apparently like 3-hour builds to get your logic on screen. It will just instantly show up within a matter of a couple seconds. And they also have this claim to fame about being able to push JavaScript to your device and do over-the-air updates so that you don't need to re-upload your app and get people to re-download that APK. So there is something very interesting about React Native that is in that very first word, which is React. And that is because React Native is just a native port of React, which is a very popular JavaScript library for building UIs. Now, the reason React is important is because the architecture of React is actually what allows React Native to be possible. And specifically, React is powered by a virtual DOM. If you don't like web dev, don't worry, you don't need to know too much about this, except for that it allows your UIs to be declarative. And what I mean by declarative is that you say what you want, and then React will magically make that so. So a normal workflow will look something like, oh, I want a view to look this way. Let me go and get that view. Let me grab its layout params, set them to wrap content or 10 pixels. Don't hardcode, that's actually bad. But set it to some size, set the background color, etc., etc. Manipulate it till it looks the way you want, and then wait for another input and do that all over again. In React, your workflow would basically just emit a desired look for your view, and then React would take care of all of the translation needed to bind that view. So it would go and get the layout params and set the size and set the color. So it looks something like this, where you're emitting a series of descriptions that you want, and the React framework is taking care of all of that lower level manipulation. Now, why do we care about this? Well, because this virtual DOM is exactly what allows React to work on mobile platforms. So we have this structure where the React code, and in our case the React native code, is creating a bunch of components. That's you writing your UI and your business logic, and then it's emitting a description of what it wants the view to look like. So if you have something that's centered or left aligned with a certain font size, it is emitting a stream of descriptions of that UI saying, please render this, this is what I want my UI to look like. And the great thing about this is totally platform agnostic. And the part that becomes specific to a platform is when we introduce translators. And so React Native has this platform agnostic piece, and then it hits this platform specific piece via the translation pipeline. And those translators know how to take a generic description of a UI and bind it down to a specific implementation per platform. So we get this really nice bright dividing line between what's platform agnostic and what's platform dependent. And the great thing about React Native is that as long as you can write translation logic, you can theoretically run it anywhere, because it's always outputting these agnostic descriptions of UIs. And so as long as you know how to take an agnostic description of a UI and bind it somewhere, you can run your React Native app. Now, React Native renders native views, which is great for interop, because obviously all of that work that we have done to date on Android views, on UI views, etc., is something that we now get to reuse and leverage. And also, if you don't have something wrapped, you can easily create it yourself in React Native. Why would you not have something wrapped? Well, probably it's custom logic to your app. You have like my custom text view, and that's not something that React ships with because nobody else uses your custom text view. So you would go in and you would wrap it, and this is pretty easy to do. So you get to reuse all of what you've already invested into your current production app in React Native. You're basically acting as like a tiny piece of this translation service when you do that. But this brings up a question of, there's this platform agnostic part and there's this platform dependent part, and the agnostic part is in these JavaScript derivative languages, and the dependent part is in not JavaScript derivative languages, and somehow they're supposed to be talking to each other, but that's kind of fuzzy about how they end up doing that. So, how do they end up doing that? Well, they do it via the React Native bridge. And specifically, if you ever wanted to poke around in this logic, it's hosted in messagequeue.js, which is a queue that is both asynchronous and FIFO, which means first in, first out. If you are there first, you get serviced first. Yay for you. Queues work. Now, this matters because we have the Android runtime, or the native runtime if you're doing things in C or C++, and we have the JavaScript core, and a lot of communication needs to happen. Just a few examples of this: network requests and their responses, layout requests and user interactions. You might need to invoke something like asking for permission and then wait to know if you got it successfully. So there is a lot of communication happening here. And you can actually, if you have a React Native app, spy on this bridge, and you'll see that all of the descriptions of the DOM are coming through this bridge as well. So there's a steady stream of these little blobs that are like, move the view 10 pixels, shape the view this way, and all of that is coming over this queue. And so that's really cool. Like, gold star for the message queue. It's doing a lot of work, should get a raise, 10/10 would recommend. But it also means that it has a bus factor of 1. And if you're unfamiliar with the concept of a bus factor, what I mean by that, and what most people mean by that, is how many people would have to randomly get hit by a bus before your project crumbles, and here it's 1. If you take out the message queue, if that gets backed up in your React Native app, everything falls apart. So no more gold star for the message queue. But there's a good reason for the fact that it needs to exist, which is that it handles all the traffic. The problem is that it needs to also handle serialization and deserialization, because we're going from these JavaScript derivatives to things that are not JavaScript derivatives, and they need to share some common way to communicate. And so they need to be deserialized and serialized on either end of this queue, and that takes time, which means that this can become a bottleneck pretty quickly. This was definitely something that I hit when I was doing React Native at my former startup, that our JS was very performant, our Android was very performant, and all of our performance problems ended up coming down to the message queue because we were trying to pass too much information between the two sides. Now, what's interesting about this is that the message queue is asynchronous, so if you start hitting problems here, it's actually not going to freeze your UI. Instead, it's going to freeze your logic. And if you think about this for a second, it'll make sense, because the UI is just run on the main thread. This is asynchronous. And so you're tapping and you're getting your nice ripple animations, and all of that is working, and it's pushing a bunch of these tap events onto the queue. But that queue is backed up, so it's not processing them. So it processes everything else, eventually gets to that, and then processes it 5 seconds later, and you do your navigation or whatever you want. So is that good or bad? I don't know. People will still be able to interact with your UI. It just won't do anything. I guess it's about the thought that counts. Anywho. That's React Native from a kind of high-level architecture. Now, we can compare that to Flutter, which is similar enough to be interesting, but diverges in some pretty key ways. The baseball stats for Flutter are that the language is Dart. It is sponsored by Google, but also open source, and it has UI plus logic, and it also has that claim to fame about hot reloading. They lean extremely, extremely heavily into this development experience in their marketing materials. It also has a very large widget library out of the box, and if you've ever heard someone talk about Flutter, you will have heard the term buttery smooth UI. Now, we talked about re-implementing versus wrapping UIs earlier. React Native went with the wrap approach with the translators and the bridge around those native views. Flutter takes the opposite approach, which goes with full re-implementation. And if I said anything, I don't know if you guys follow WWDC or anything that happens in the Apple world, but every year for WWDC they have this keynote bingo, and you can do bingo because they just have these really repetitive phrases, like anything with a Johnny Ive voiceover every single year. And if I had to do this for Flutter, you could like get rid of all of that and just replace it with a single phrase, which is like, this would be Flutter keynote bingo. And the reason that I hone in on this is, and to be fair, the Flutter team has moved away from this in their marketing materials. It's no longer the only thing they talk about, but it used to be, so sorry, Flutter. But the reason they lean into this is that their architecture is actually built specifically to optimize for this problem. And it shares this with another industry that I know nothing about, so it's great that I'm referencing it in a presentation where I'm supposed to be an expert, which is the gaming industry. They care a lot about graphics and throughput, and if you know anybody who's into games like I happen to, they talk about GPUs a lot, which are kind of, you know, like the less great CPU in that they're not quite as powerful, but you can parallelize a lot and they can get a lot of stuff done. And so the gaming industry leverages these to get smooth UI, and Flutter leans really heavily into this too. Caveat, Android has hardware rendering. I don't mean to say that they don't, but Flutter leans extremely, extremely heavily into this GPU ideology based on its architecture. So what does that look like in implementation? Well, in Flutter, you have this widget layer where you're creating your UI. It's very much like the components in React Native. And then you have some interpretation layer that I'm going to hand wave on for a second. And then it outputs directly to a Skia canvas, which goes into the native canvas and gets rendered. Now, that interpretation layer that I hand waved over, what it's actually doing is it's generating a layer tree. And this should sound very familiar from what I just went over with the React Native architecture, which is that it is platform agnostic. The layer tree is very similar to those DOM descriptions in that it says, I want a view that looks somewhat like this, and then it sends it off to Skia, and Skia will actually handle the drawing commands for that. Now, this is really cool because once again, we have a very clear separation of concerns between the UI task runner, which is what this would be called in Flutter, and the GPU task runner, in terms of we do all of our Dart and all of our layout in this UI task runner, and then it gets sent off to the GPU task runner where we can do all of our rendering. And those two things are in separate threads depending on how you init these task runners. They can be in separate threads, so you can parallelize really well, which means that you can be working on the GPU at the same time that you're preparing the next frame to lay out and render. Now, there's great resources online, so I'm not going to go further into that. You can check it out. But what you should be noticing is that there is no view or UI view here, and that's because, of course, Flutter has decided to re-implement everything. And this is where that widget library comes in handy. It's not like they were just feeling generous and decided to give us a ton of widgets. It's because we need them. Like, there's no way for us to use any of the existing library. So the reason they give us such a huge and robust widget library is that without them, we would have nothing to render. We would have to literally be like drawing on a canvas ourselves. So, because they decided to take on a lot of complexity by completely re-implementing the view system, There are two parts to the Flutter architecture. They didn't bundle it all as one. So there's the Flutter framework, and then there's the Flutter engine, and if we're actually being real, there's also this embedder piece, but I'm going to skip that for now. So there are two main pieces that we're going to talk about. The Flutter engine contains the things that you would consider lower level, so Skia, the Dart VM, task runners, method channel support, etc., etc. And a side note on task runners, the Flutter engine requires you to init with 4 different task runners. So there's the platform one, in which all of the Flutter engine work happens, and the platform task runner is actually backed by the main or UI thread, which is funny because there's also a UI task runner which you would think would be run on the main or UI thread, but the UI task runner in Flutter is actually responsible for all of the Dart code, because that is where you are describing your UIs, and so this can be done on a different thread, and then we have our GPU runner and our IO runner. So that's a little aside about kind of how we structure work and these different channels that work is happening to. And the first 3 are extremely locked down. So like only Flutter engine work can happen on that platform task runner, only the Dart work can happen in the UI, and only GPU work can happen in the GPU task runner. IO is kind of the Wild West. But that brings us to the Flutter framework, which is probably where you live and where most developers would live, and this is where all of the actual application code would happen. So you're building your widgets, you're handling your logic, animations happen here, and you're just spitting out this layer tree which describes what you want rendered. A few things to note here are that the Flutter system leans extremely heavily into immutable and composable views, and they call them widgets, not views. And everything is a widget, and by everything I mean literally everything. So if you wanted to have a text view that was centered, you would put a text view widget into a centered widget, and yes, center is a widget. So there are some things that are nice about this, which is that, one, it enforces good state management practices because everything's immutable and flowing in the same direction, but also Dart enables Flutter to have a really good developer experience because they get to do some fun like tree shaking things with Dart language that Kotlin or things like that don't support, although when it actually packages and ships, it's ahead of time compiled. But it does not have something that React Native has, which is those OTA updates, and that is specifically because of the choice to use Dart. And I should say that this has not happened yet. It is technically feasible. The problem is that Apple only allows you to do these OTA updates in the form of JavaScript. Dart is not JavaScript. Dart can compile to JavaScript, but someone would actually need to do the work to have that happen and then integrate those OTA updates. So this is not something that Flutter can do in the same way that React Native can do yet, although theoretically in some future horizon that is possible. Now, there is the same issue with Flutter that there is with React Native, which is that you have your Dart and you have your platform languages, and those need to figure out how to communicate, and they handle it in much the same way, which is via method channels instead of the React Native bridge. And there are some like little differences. The message channel in Dart actually invokes on the main thread as opposed to the React Native bridge, which is asynchronous. It is asynchronous, but it invokes on the end on the main thread. And so they're also accessed via like named strings and things like that. You're creating one-off, but it's a very similar overall paradigm, which means that it can be prone to the same sorts of issues that I covered in the React Native bridge. Now that brings us to the last architecture, which is for Kotlin multi-platforms. If you've ever wondered what MPP stood for, this is multi-platform projects. I had a lot of people tweet me asking about that, so now you know, right there. Now, if it had a baseball card, it would look something like this. Surprisingly, Kotlin multi-platform is written in Kotlin. I know you didn't see that coming. It's okay. It's okay. It's sponsored by JetBrains, but also open source. I know, surprise. And what's interesting is that this falls into that third bucket of cross-platform technologies, which is the logic-based one. Now, the claim to fame here is something that I find really intriguing, which is that literally its only claim to fame is that it's in a language that people already love. And this seems so weak compared to the claims to fame of the other platforms where it's like, get rid of your whole development team. If you write Flutter, you only have to write it once, or like hot reloading or over-the-air updates. That seems really compelling and way more compelling than this, hey, you can write in a language you already use. But I don't want to minimize this because it's actually hugely important and influential. And to illustrate that point, if you aren't aware, Dropbox wrote recently about their move away from C++, and a very driving factor in the reason they did that was that they didn't have C++ experts on staff, and it became a huge overhead for them because they were using this technology to share logic code and didn't really know how to maintain it or to make it work, and that was purely because it was in this language that they did not know. And so while this seems like a very small thing to emphasize, it's actually really important in practice. Now, I can't talk about MPP without also talking about Kotlin native, and there's a lot of confusion around this point. So just to give like a high-level overview, MPP is the act of targeting multiple platforms, whereas Kotlin native is a way to target different platforms. Specifically, we usually refer to Kotlin native in the form of it's what we output to target iOS. So Kotlin MPP, like if you're targeting multiple platforms, you can do native, JVM, JS, etc. This is kind of the relationship between these two terms. Now, what is Kotlin native though, which I think is also a point of confusion? It's basically just something which can output a native binary that runs without a virtual machine. Why do we care about things running without a virtual machine? Well, it stands in contrast to this extremely abridged Android build system. Someone at Google is cringing right now that I put this on a slide, which basically has, like, you have your Java and Kotlin code, it compiles into class files, the dexer takes those in, outputs dex files which contain the Dalvik bytecode, and then that runs on the virtual machine. In Kotlin native, we don't have that VM layer, we just have Kotlin with our compilation, which outputs a executable that you can run specifically on whatever it was targeted for. So if you're running a native binary on Windows, that's not portable in the same way that something that was targeted at a virtual machine would be. So how is it actually used? Well, Kotlin native targets interop specifically with C, and there are some tools that help you do this. So when Kotlin native wants to interact with the world around it, you define the ways in which it interacts with things outside of it in a def file, and then you generate these bindings with a tool and you package them together with that executable, and then when you do something like that, you can get your workflow where you can deep link into things and have autocomplete, etc. This is how you can take your Kotlin native and put it somewhere that it doesn't belong and still have a nice developer workflow. Now, luckily, you don't usually need to do any of that step. It is happening, but it's happening for you because JetBrains has written a lot of platform libraries that are there by default. Specifically, they ship POSIX by default, which is the Portable Operating System Interface. I think someone can fact check me on that. And then also Objective-C bindings and things like that. These are written for you. So JetBrains has gone ahead and kind of done this translation layer for you so that your Kotlin code can interop with anything that is C or C derivative. Which brings up the question of why do we care about Kotlin interoping with anything that is C or C derivative? Well, iOS apps are written in Objective-C. Objective-C is a derivative of C, and ergo, this is where the magic happens. Now we can do our cross-platform work. Now, if any of you work in iOS, you're probably looking at this statement and being like, whoa, slow down, what about Swift? And actually, now that you have heard the last few slides, you can probably answer this question on your own, which is that Kotlin native targets interop with C. Swift is not a C derivative language, so directly using Kotlin native with Swift is not actually supported. You need to export your API to Objective-C first, which does not mean if you are a Swift app writer that you cannot use Kotlin native. It just means that you can't do it without Objective-C, at least a little Objective-C defining this API layer, because we need a way to translate. So this is actually a lot of languages on the slide. Like, I'm talking about Swift and Objective-C and Kotlin. Worst case, you have 3 languages. All of these languages support different feature sets, which should be worrying people for very good reason, because it means that the features in these languages need to be mapped to each other. And this is like a small subset. This page, if you wanted to, like, scrolls infinitely. It could be like one of those things that puts you to sleep at night, just like casually scrolling past and lulling you into a sense of dread. And this is actually a real problem, because in the other cross-platform technologies that I talked about, there was this single locus point for where we were taking two different languages and connecting them. So they were happening like in the React Native bridge or in the message queue. This was our locus point for communicating, and everything was serialized on one end or the other. What's happening in Kotlin Native is that we actually have an entire API layer that we have to worry about, where when you're calling into something, this is either happening explicitly where you're boxing something into like a Kotlin integer, or it's happening implicitly where the technology is doing this under the surface. But regardless, your API surface for these translations is actually huge, as opposed to that single locus of a bridge where everything is forced to be serialized at this one specific point. And this leads us to this problem of like, if it can't be mapped, it can't be used across these boundaries specifically. And this would be extremely, extremely limiting if you think about it, because it means that we would only be able to take the subset of what all cross-platform targets that we wanted to target implemented. And this would not work for anybody in practice. And so what Kotlin Native has done from an architectural standpoint and implementation standpoint is it has specifically decided it didn't want to re-implement and encompass the entire world. And it allowed us to kind of have this safety valve, which is the expect and actual keywords. So how these work is that your common code, the code that's shared across all of your platforms, will be able to say, I expect some functionality to be there, and your platform-specific code will be able to meet that expectation by providing an actual implementation. So this is very similar to an interface in that the common code can invoke the function, it doesn't care how it's implemented, and the platform code will provide the actual implementation. If you look at documents, the easiest way to think about this is with the print statement, which is what they use in their example. So if you're in JavaScript, print is implemented by like console.log, whereas if you're in your Java world, then it's system.out.println. And so here in your common code, you would say, there's a print function. And in your platform code, you would either do console.log or system.out.println, depending. So this is a safety valve in that it allows us to proceed without things existing in one platform or another. This is important because like generics vary very widely between Java, Kotlin, Swift, and Objective-C. So if you were in this subset, you wouldn't be able to do most of the fun things you want to do. But it also acts as an accelerator in that when you have the ability to keep things in the native implementation and not need to implement them in MPP, you can roll into a multi-platform solution as things get built. And this is very, very important because MPP is much younger than any of the other platforms that I've talked about today, and so a lot of things have not yet been built. So like we're just getting the DB support, we have KTOR for networking, but a lot of the systems that we're used to that have already been built out for Android in the JVM world have not yet been ported to MPP, and it's like this wild, wild west where things are kind of missing. And so if you had to wait for everything to be built, you would never be able to adopt this technology right now. But what you can do is you can use what is possible in MPP in that cross-platform common package, and then as things get added, you can move things across this boundary and kind of inch it up and widen the scope of your common code without having to go all in today. So what does this mean for your Android code? Well, mostly everything stays the same, except for that you get really conscious of what's in the JVM and what's not, because you can't reference JVM provided utilities in your common module, otherwise it wouldn't be able to port to iOS. And what it looks like for iOS developers is that they now have some framework that gets output that they link against. Specifically, they would have to go into Xcode and link and put it on the search path, but it's just a dynamic lib or a framework that you're linking against. So actually a lot doesn't change for them either. The biggest portion of the work is in actually creating this framework. Once you've created it, the platforms can use it much like any other dependency. If you need to update, you regenerate the framework, etc. One big thing to call out is that this is experimental. So React Native and Flutter have a ton of resources to throw against them. They're pretty mature right now, although obviously still developing very quickly. MPP is much, much earlier in its timeline, although it's also developing very quickly. And that's not to say that you shouldn't use it or you shouldn't consider it. It's to say that if you do use it, you need to expect what happens when you use experimental technologies, which is that they change very rapidly. So that was a quick look at the architectures of these three. I very purposefully, like I said, tried not to insert my own opinions because they're not actually that great, but also because I wanted to give you time and space to have your opinions. So hopefully now that you've seen the architecture of these three, you might have an inkling in your mind about whether you're team Reample or team Wrap, whether you're team Bridge or team Map. And to be honest, you can be any of these things and be a great developer because there's no one real right answer. Like, I can't tell you which one's best, but I hope that having watched this and understanding a little bit more about how these are architected gives you the ability to make your own decisions. Thank you.